Hi everyone, it is my great pleasure to present this project of the optical research group at UCLA. My name is Junxi Li, and my research topic is the spectrally encoded machine vision using trainable materials. Here is an outline of my presentation. First, I will briefly introduce the background of this project, the diffractive deep neural networks, and then I will focus on the motivation of our new work, explain the new methods we use to solve the problem, and show the numerical and experimental results we achieved. Finally, I will give conclusions and future perspectives. In recent years, engineering of materials has opened up new avenues for performing many kinds of computational tasks optically, which is achieved through designing new components and devices based on spatially devised matter interaction, all the way from solving equations to acting as neural networks to perform machine learning inference. These approaches highlight the emergence of engineered material as a building block of optical computation. Considering the rapid advances being made in deep learning and machine vision applications, there is a growing need for optical computation in order to benefit from the low power, low latency, and scalability that this passive optical system can offer. Among these reported frameworks, diffractive deep neural networks, or DSQRN, is one that can perform optical machine learning inference or optical component design tasks. As shown in this slide, DSQRN is composed of successive diffractive layers, which have neurons modulating amplitude or phase of the light field and can be trained using deep learning. The complex wave field coming from the coherent light source propagates through all these passive diffractive layers, so that the intensity at the output plane will be distributed in a desired way. Once the training of these diffractive layers is finished, we can physically fabricate these layers and stack them together to form an optical neural network. This network can execute the trained function at the speed of the light without use of any power, except for the illumination light and the output detectors. Many early studies conducted on this framework have shown its statistical inference capabilities for machine vision, achieving an accuracy of over 98% and 89% numerical blind testing accuracies for the classification of the images of ominous handwritten digits and fashion products. Without use of any nonlinear activation function, this diffractive framework still shows depth feature, for the reason that statistical inference and generalization capabilities improve with additional diffractive layers, which was demonstrated both empirically and theoretically. Besides, we also demonstrated this framework as a tool for designing deterministic optical components to perform, for example, optical imaging, as shown on the right. Recently, this framework has also been extended to design broadband diffractive optical systems, and one of the applications of this is to design a spatially controlled wavelength multiplexing system. In this one shown on the left, with a pulse source that has a broad frequency range, these passive diffractive layers, trained through deep learning, can direct 4 different spectral bands to 4 spatial positions at the output. In another recent publication, we also demonstrated the usage of this framework to perform pulse engineering, where the diffractive networks are used to shape an arbitrary broadband pulse into a desired optical waveform, forming a compact and passive pulse shaping system. Okay, so before my introduction of our new work, let's first think about one problem in designing machine vision systems. The modern machine vision systems are usually composed of several major parts. The first one is a lens-based optical imaging architecture that can relay image of a scene or an object onto an optoelectronic sensor plane, which usually demands a high pixel count sensor array to capture sufficient spatial information. The other one is a back-end digital processing unit, which is used to extract target features from the acquired image information and perform specific machine learning tasks, for example, object recognition. However, this traditional process has some drawbacks. First, high pixel count sensor arrays have in general a large latency between the successive frames due to the time required for readout and digitization, which substantially hinders the frame rate. In addition, unlike the visible light, high pixel count sensor arrays are challenging to fabricate at some parts of the electromagnetic spectrum, such as far and mid-infrared and the terahertz bands. Moreover, the inference model of the back-end digital neural networks must cope with the high-dimensional input data, and in most cases, this data contain redundant information for assigned computational tasks, which results in a high computational burden and inefficient use of the resources, for example, power and memory. So for designing the next generation of machine vision systems, considering the diffractive network's powerful optical information processing capabilities, we can transfer some parts of the back-end digital processing unit's labor to this diffractive optical neural network, and we'll be able to use lower pixel count sensor arrays to receive the output from the optical front-end. By introducing the broadband diffractive optical neural networks that are mentioned above, we can further shrink the sensor part to be single pixel, such that we can benefit a lot from this single pixel detection scheme that are low latency, resource efficient, and easy to fabricate. Also, the back-end digital processing unit can be structurally simplified and boosted in the computational speed due to its lightened burden of handling smaller scale of input. So following this design strategy, here in this work, we present a single pixel statistical inference framework that replaces the conventional imaging optics of a machine vision system with a series of diffractive layers forming an optical network. Given an object or a scene illuminated by a broadband source, the presented framework relies on the trained diffractive layers to encode the spatial information of the object field of view into the power spectrum of the diffracted light. This is noteworthy that this spectrum is corresponding to a set of predetermined wavelengths as shown here, where each wavelength represents one data class. In this way, the network can conduct all optical inference based on the wavelengths that has maximum power detected by this single pixel spectroscopic detector, like this wavelength for 8 here. Furthermore, we can feed these spectral class scores as an input to a shallow artificial neural network that has 2 hidden layers to reconstruct the image of input object, decoding this spectral encoding performed by our broadband diffractive network. Overall, this unique framework can achieve task-specific spectral encoding of spatial information and allow us to optically to perform machine learning tasks, for example, image classification and compressive imaging, by using only a single pixel spectroscopic detector. We demonstrated the success of this machine vision framework through a set of trained diffractive networks that are composed of 3 layers. After 3D printing of these resulting diffractive layers, we experimentally validated the success of these single pixel image classification systems by classifying handwritten digits at the terahertz band, using a snapshot broadband illumination and a plasmonic nanoantenna-based spectroscopic detector. Based on this experimental setup, we take the models that achieve the numerical testing accuracy of 95.05% on classifying M-list digits, and in this figure show the comparison between the power spectra that were numerically simulated using our trained model, which is dashed line, and its experimentally measured counterpart, which is the straight line. These results provide a decent match between the two, and also show the correct class inference in each case. This slide shows the confusion matrices of the numerical testing accuracy and the match between the experimental and numerical testing of this diffractive network design. Despite 3D fabrication errors, possible misalignments, and other sources of error in our setup, the match between experimental and numerical simulation was found to be 88% using 50 handwritten digits that were 3D printed. Besides this model, to further evaluate the match between our numerical models and their experimental counterparts, we also 3D fabricated and experimentally tested 2 additional models that have the same architecture as the previous one and also were trained on the same dataset. By tuning the coefficients in our loss function, during the model training, the balance between the optical inference accuracy and the diffractive power efficiency at the output detector is shifted in these two new diffractive designs in favor of different experimental robustness. For example, in the one design that achieves the blind testing accuracy of 84.02%, the diffractive power efficiency is increased by a factor of around 160. The match between our experimental and numerical testing results are increased to 96%, demonstrating the trade-off between the inference accuracy, the diffraction efficiency, and the experimental robustness of our diffractive models. To provide a mitigation strategy for this trade-off, next we introduce the collaboration between the diffractive network and its corresponding reconstruction neural network. This collaboration is based on the fact that our decoder artificial neural network can faithfully reconstruct the images of the input objects using the spectral encoding, even if the optical classification is incorrect, pointing to a wrong class. We observed that by feeding the decoder neural network's reconstructed images back to the diffractive network as inputs, we can have it correct the initial wrong inference. Through this collaboration between the diffractive network and its decoded artificial neural network, we improved the overall inference accuracy of a given diffractive network model. For example, for the same highly efficient diffractive network model, the blind testing accuracy for ambulance classification increased from 84.02% to 91.29%, demonstrating a substantial improvement through the collaboration between the decoder neural network and the broadband diffractive network. The performance of the presented spectral encoding framework can be further improved using a differential classical encoding strategy. For this aim, we use two different wavelengths to represent a spectral class score vector. We considered encoding the spatial information of an object into 20 different wavelengths, which are paired in groups of 2 in order to differentially represent each spectral class scores, using formulas shown here. With this spectrally encoded differential classification scheme, we numerically obtained 96.82% optical classification accuracy for handwritten digits. In this table, we summarize the performance comparison of different loss functions employed to train the decoder artificial neural networks, and their impact on the improvement of the classification performance of the diffractive network. We see significant improvements in the inference accuracy when the artificial neural network has been penalized during its training, if its reconstructed images cannot be correctly classified by the diffractive network. In summary, in this work, we demonstrated an optical machine vision system composed of trained diffractive layers that is used to perform optical classification of unknown objects with a single pixel detector. Also, shallow and low complexity artificial neural networks can be used as decoders to reconstruct images of the input objects based on the spectrally encoded class scores. We believe that this framework presented in this work would pave the way for the development of new machine vision systems that use spectral encoding of object information to achieve a specific inference task in a resource-efficient way. This work can also be extended to spectral domain interferometric measurement systems, such as optical coherence tomography, to create new 3D imaging and sensing modalities. While our presented approach utilizes only the native dispersion properties of the 3D printing materials, we also envision utilizing metamaterials and their engineered dispersion to design diffractive spectral encoding systems with additional degrees of freedom. Finally, I would like to thank my advisor, Professor Oskan, and the other group members, as well as the funding agencies for the support to our work. Thank you for listening.